Morning, everybody, and welcome back. So the topic this week is to have a more thorough discussion of gradient methods. And this is something which also becomes very important when we are beginning with project number 2. So in project number 2, we are going to write our own code for neural networks. And hopefully today we will get started with neural networks so that we start scratching the surface and look at the basics of a neural network. However, what we are going to do today is more to go through some of the famous gradient methods or implementations of approaches to the learning rate, which is perhaps a better way of stating it. Now, this lecture is going to be a kind of mix of us running Jupyter notebooks and also some jumping back and forth into the whiteboard. But it will be a large fraction of the lecture is actually going to deal with just running codes and looking at how we can implement things. So this week, we don't have any exercises. We're just going to focus on the project. And as you can see from the suggested weekly schedule, the topic today is also to, after gradient descent methods and stochastic gradient descent, we are going to discuss automatic differentiation, which is a method, it's a famous algorithm, which really saves the day when we are dealing with machine learning. And we are going to see some examples, and we are gradually going to bring in more and more examples on how you can use automatic differentiation. And there is a library which we are going to encounter. The first one is called AutoGrad, but that has been replaced by JAX, J-A-X, which also includes just-in-time compilations, and it actually speeds up most Python programs. And it's widely used in machine learning connections. And it includes automatic differentiation. We're also going to demystify a little bit what automatic differentiation means with some simple examples, but we are going to repeat this again and again when we come to neural networks, because that's where you will really see the benefit of being able to switch between different cost functions without going through the hassle of every time having to hard code derivatives, etc. So this really is something which saves the day, and it's a tool which you will find useful in many, many other cases as well. In particular, if you need to calculate derivatives to numerical precision. And you can simplify the operations in terms of well-known mathematical functions like exponentials, cosines, sines, etc. So there are, as usual, there are some videos. I also wanted to point to what we will discuss next week, which is now linked with neural networks. And you will find in Rashka's textbook in chapter 11, there is actually a discussion on how we build up our own code for a neural network step by step. And these are things which we'll also go through during the lectures and the lab sessions. So in a certain sense, although your mind is now directed towards project 1, we are bringing in elements from what comes in project 2. And one of the things you're going to do in project 2 is actually to start writing your own gradient descent method. So that's going to be a part of project number 2. Okay, the lab sessions, there is no kind of exercises this week. It's only project work. And the deadline is next Monday. So let's have a quick summary from last week. So when we discussed these gradient descent methods, what we did last week was to discuss gradient descent, plain gradient descent, and gradient descent with what we called momentum. So I'm going to repeat some of these elements. And one of the problems with gradient descents is that it's actually very sensitive to initial conditions. The gradients are computationally expensive, which means that it actually requires a lot of time to calculate the gradients for large data sets. They're also sensitive to the choices of learning rates. And it treats, the gradient descent treats all directions in parameter space uniformly. So these are some of the major drawbacks, which we are coming back to today. But let me quickly remind you of some of the things which we did last week. So when we set up the algorithm, so we are going to switch now to the whiteboard, and let's quickly remind ourselves. It seems, by the way, that my pointer keeps disappearing here. Ah, there it is. Just a moment here. It's probably the setup with the screens here, which is taking out my pointer. There we are. So if we just remind ourselves a little bit of what we did last week. So we discussed gradient descent and gradient descent with momentum. And gradient descent with momentum is something which you would implement irrespective of method you're doing. So the basic algorithms which we discussed last week is something which we just called gradient descent with a constant learning rate. And so GD stands for gradient descent. And we had gradient descent with momentum. So if we look at the basic algorithm, which we had for gradient descent with momentum, GD with momentum, and it's easy to reduce that one to just plain gradient descent. So the first thing which we would do then would be to fix a learning rate, define the learning rate, which we call gamma. And then we would initialize the unknown coefficients to random values, the beta parameters. We would fix a number of iterations, set number of iterations. And this would essentially be, besides the other initializations where we have set up the design matrix and all the parameters which we need for the problem, these will be the parameters which we need to initialize when we start a gradient descent method. And then we would have a loop here for number of iterations. And while the stopping criterion has not been reached, while not reached a stopping criterion, what we would do then, when we do this with a so-called gradient descent with momentum, I also forgot actually to set the parameter delta, which we define, set the parameter delta, which is now a parameter between 0 and 1. So when we do this, the first thing we defined was this parameter v of I, which was then given by delta of beta of I, the new value, minus beta of I minus 1. And these are the iterations, so we're putting parentheses around here, minus gamma, and then we had the gradient of with an input value of beta from the new iteration with step beta of I. With that one, what we would do next is to calculate beta of I plus 1, which would then be given as beta of I plus this v of I, which we defined in the previous step. So v of I is an intermediate step. And if we don't have a momentum added, so with no momentum, then this V of I is just minus G times gamma of beta of I. So if we don't add momentum or just put this delta equal to 0, then we have a simpler expression. And what we end up with then is also to have a stop criterion. So stop if we take the absolute value of all the beta of i's plus 1 minus beta of I smaller than or equal to a parameter epsilon. And this epsilon can be something like 10 to the minus 5 or even smaller. And this is now an end while here. So that's the basic element of a gradient descent with momentum. And it's actually pretty simple to implement. So let's just remind ourselves of some very, very simple implementations where we now are putting in the expressions for the gradients. And what I've added to the lecture notes, so if we now go back, so let's go back here. If I can find my pointer, here we have my pointer, there we are. So we should have my, okay, so let me just do one thing here. Actually had another one. So sometimes when I have a full screen, here we are. So let's do that one. Sometimes when I set up this system here, it's as if it, with the HDMI cable coupled, it's as if it takes away my pointer, it hides it. So let's now. Okay. So if we now scroll down a little bit here and look at some of the simple examples which we studied last week. So we have a data set with X and Y, a pretty simple second order polynomial. We would fix a learning rate. So this is actually one of the brute force ways of doing that. And the typical approach is that you would set up a whole range of such learning rates and then simply try around and find the one which gives you, for instance, the best mean squared error when you're training your models. Then we set just a number of iterations to 100. So this is a pretty simple program. And in this case, we are dealing with the standard ordinary least squares. And observe also that I haven't put in a stopping criterion here. So some people also put the stopping criterion on the gradients being close to 0 or equal to 0. So in principle here, we should also have a stopping criterion. Now, this is the standard ordinary square. So this is a derivative of your cost function, which is just a mean squared error. Then you have lasso and ridge. And there's one thing which you could actually have coded lasso if you wanted. But we thought we could use scikit-learn's functionality because that has often some better search algorithms as well. So scikit-learn uses a gradient descent when it solves the lasso equation. So if you wanted to implement it, it's actually not that difficult. And in the code here, just for the sake of completeness, I have included the equation for lasso. So first is ridge. So we put in the matrix, the identity matrix, which is this one. And this is the gradient for ridge. Now, later today, you will see how we can do this with automatic differentiation. So that means that this equation for the gradient, which you see, is something we can just call a function. And the only thing we feed in is the function we want to optimize. And I will show you that quickly in an example as a small teaser for how you can include automatic differentiation. So just pay attention to what you have here is you hard coding the gradients. And this can easily be error prone, especially if you have a more complicated expression. Now, for the sake of completeness, I've also included lasso here, as you can see. And lasso has the same mean squared error. So the first term here is just the mean squared error, except that now I have beta ridge and beta lasso. I'm also doing something which does not favor lasso and ridge. I'm including the intercept. So I may penalize the training. But this is just meant as an example on how you use a plain brute force gradient descent. And lasso is something you could have included very easily by simply taking the sine of the parameter beta. This is actually the derivative of the absolute value of beta. So this is the way you could have included if you wanted to write a code yourself. And in this specific case, when you run the code, you see now that since I don't get exactly 4, so the parameters I should have gotten are actually, if you look back to the function, I should get 4, 3, and 5, but I'm having few iterations and I have a parameter eta, which may not be the optimal one. So typically the way you would set things up is to actually have a chain of parameters, a grid of parameters, 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, to let's say 10 to the minus 1. If you go beyond 1, then you will often have very, very unstable results. So the results you will see here when you run these codes will obviously depend on the parameter eta, or the learning rate, and obviously the parameter lambda, which we use in ridge and lasso. So this is the way you would set up ridge and lasso. And here you see the result you get when you now optimize with only 100 iterations. Okay, so this is just a quick summary of what we did. But now what I wanted to have here is to set up Newton's method. So this is the same function, but now I have defined the cost function I want to optimize. And this is meant as a teaser for automatic differentiation, okay? And we are coming back to it. So I have defined the cost function, as you can see in the Jupyter notebook here. And then now I'm calculating the inverse of the Hessian matrix, because I don't need now to set up a learning rate. And you can see now that I'm setting up the Hessian matrix, the definition here, and I'm performing the standard linear regression, ordinary least squares, where I take the inverse of the matrix. So this xt underscore x here is just the transpose matrix times x. This is my Hessian. And note that this Hessian matrix does not depend on the parameters beta. So I can actually invert that once and for all. Now, the problem with logistic regression is that logistic regression depends on the parameters beta for every iteration, which means that I would have to invert the matrix for every time I update the parameters beta. So if I then use automatic differentiation, which is the old variant, so this is called autograd, as you can see here, I import that library, and then I import the gradient. And you see now that I can now define the training gradient instead of me hard coding the gradient. I now let automatic differentiation calculate the gradient for me. And this is something which takes some few more CPU cycles, but it takes away all the hassle, because when you develop something, you have to think of not only compile time and run time, but you have also to think of development time for the whole project. So if it takes you days to arrive at the analytical expressions and some time to decode and make sure that everything has been coded correctly, then you have to add that to the total time you spend on performing the calculations. So if you now just define the cost function, as I've done here, with a mean squared error, as you can see, this is the one which I defined here, cost ordinary least squares. And then the only thing I do now is simply define the gradient, and then I calculate the gradient as a function of beta here. And if I run this code, what you will see now is that own inversion gives this. And these are the gradients which I have after some few iterations. And you see now that after just 1 or 2 iterations, my gradients are 10 to the minus 17, which basically means 0 in numerical precision. So I just wanted to bring up this automatic differentiation as a small teaser, because we are going to spend some time on it later today. And you see here that with Newton's method, if you can calculate the Hessian matrix, if that is possible, then you should do it. Because then you don't need to fix a learning rate. And if it doesn't take too many cycles, so if you have a matrix which is, let's say, 30 by 30, and you're doing ordinary least squares or something like that, then you can quickly actually calculate this Hessian matrix. And if you're dealing with lasso, you actually have to calculate the gradients anyway, numerically, because you have this sign which you have to deal with when you take the derivative, which means that you don't have a nice analytical solution for the parameters beta as you have with ridge and ordinary least squares. Any questions, guys? So Newton's method, if you can do it, you should do it. Now, the next case is actually a logistic regression with gradient descent. And in this case, so there's something which we haven't stressed too much when it comes to the projects, is whether you should object orient or not. This is not something which will penalize you if you don't do it, because many of you have different programming backgrounds, which means that not everybody is fully familiar with it. But we are going to put in examples from now on how you could object orient it. So here you could actually make a class for logistic regression. And this specific class here takes the number of iterations. It has a fixed learning rate. And in this case, we have this sigmoid function, which we discussed last week and the week before. And here we do a gradient fit. And you can see now the gradient fit without automatic differentiation. We are now calculating the linear model with a design matrix times the parameter for logistic regression. The predicted value is the one we get from the sigmoid function. And then the gradient is the expression which we calculated in the lectures last week and the week before. So the gradient descent part is actually what you see here. It's essentially the same as before, except that now the gradients change. So you could have used now automatic differentiation, but this is the way we would hard code the expressions we discussed the previous week and the week before, when we introduced logistic regression. So you see, when you do gradient descent, it's actually, it's something which is pretty easy to plug in. It's just some few lines of code. Now, this specific case is actually a case where logistic regression fails miserably. And we are coming back to this. This is a so-called AND gate. Are you familiar with what's an AND gate? So in the inputs here, what we have X and Y. So if we go back to the, I'm just going to set this up here so that you can see it. So let's just exit the full screen, change sharing, and then we go back to the, there's my pointer again. I have to, here we have my pointer. So the case we are looking at is something which we will bring up again. And this is called an AND gate. And probably you have met something which is called a NAND, but also an OR gate or an XOR gate. So in this case, what we have is some input, which we can call X and Y. So this can have bits 0 or 1. And then there is an output here. So let's just call this output for Z. So that means that what we would do now is to set up a design matrix where we have X here and Y. So we have two features, the two input variables, 0 and 0. We can have 0 and 1. We can have 1, 0, and 1, 1. Now, the output which we get then from these cases is 0, 0, 0, and 1. So this is an example of a gate which we are going to encounter again and again in many applications. So we have something which is also called an OR gate, an XOR gate, etc., etc., and many different combinations from electronics. Now, the thing you have to, which becomes interesting for us now, is that when we train this specific model here, these are the input variables, and this is the output. But now we have 4 different cases. Now, what we could have done now is to repeat this design matrix again and again. So we could think of making many different training cases, but where the outputs are essentially the same. They have to be the same. So we could just augment this design matrix. So now we have 4 entries, but then we could make something, we could double it. We can multiply by 3. So we can make 12 inputs, 16, etc., etc. Because then we would get more training data when we are training either a logistic regression case, which has only output 0 and 1. Now, in the case which we have here, so for this specific data set, the result is not very impressive. So if we now go back again here and look at the screens. Oops. There we are. Okay. So if you look at this case, the predictions we make, instead of having 0, 0, 1, we just get ones all the time. So this is something we are coming back to. Now, there is a very important reason for why I bring up this example. And that's because a logistic regression, as you see it here, is the same as a neural network without hidden layers. So if we take away the hidden layers and have just one specific function which takes the input and then sends out an output, this is going to be our first encounter with the neural networks. And when you write a code for neural networks, if you take away the hidden layers and you just have the inputs, which then gets modulated by a function and spits out an output, and the modulation is done by the logistic regression function here. When you do that, then what we are going to get is exactly a neural network without hidden layers. So if you have a neural network code, you can actually implement logistic regression by simply stating that we don't have any hidden layers. That's just another way of coding what you see here. Okay, so what I wanted to say a little bit about now is the so-called stochastic gradient descent. Now, if you look back at the way we calculate the gradients here, in particular these expressions which you see here, this expression means that we run over all the data. One of the problems we can risk when we run over all data like this, depending on where we start, is that we can easily get stuck in a local minimum. So one of the things we would like to avoid is something which looks like this. And so let's switch back to the whiteboard again. I'm going to jump a little bit back and forth between the whiteboard and the Jupyter notebook. So if you look at a data set where we want to find the optimal value, so we could now think of having a function which is our cost function, which depends on just one parameter beta. And the function which we would like to optimize could be something like this. So let's just suppose it looks like that. And there is a global minimum which is the one we would like to reach, which is this one, which we can call the beta ideal. And this is where we would like to be. However, when we now start a gradient descent, we have a guess. So we could guess on a value of beta, which is here. So this could be our beta 0. Now, if we then run the gradient descent with that one, with an appropriate value of beta, what could happen then is that after some steps, so the next step we would be here, 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 so that goes down with a gradient, and then we reach this point here. Now, clearly then, your gradient won't change, and your iterative process would then stop. And your fancy gradient descent algorithm would simply return the values which you have at that minimum, which is a local minimum, which is an unwanted point. So we would rather like to find ways of exploring all these possibilities. So that means that when we do this stochastic gradient descent, we're actually splitting the data which we have in small blocks, so-called batches. And then the idea is, when we do that, first, is that when we reduce a data set where we calculate the gradient for, the number of entry points in the gradients is smaller. So if you do a matrix multiplication, and your matrix is quadratic, so a matrix multiplication, if you have a 10 times 10 matrix, this requires on the order of 100 floating point operations. Or if you have an n times n matrix, it's roughly n squared floating point operations. That is what is required when you run a calculation of a full matrix multiplication. So if you now think of your gradient, that is going to contain the design matrix transposed times the design matrix. And every time you calculate that one, you have to run a certain number of floating point operations. And the more data you have, the more time expensive this becomes. If you now split everything in smaller blocks, which we are going to call batches, then we can reduce the amount of time which is required for the matrix multiplication and for the matrix vector multiplications, because the number of components is going to be smaller. So this introduces a new parameter, which is called number of batches. So that means that we are going to split the data set randomly in a certain way. And then we are going to calculate the gradients for these different small areas. Then we are going to repeat this experiment again and again. So at the end, your gradient becomes an average over all the experiments you run. And the hope then is that you can reduce this kind of situation where you get stuck in a local minimum. So let's take a look at what gradient descent typically, or stochastic gradient descent, actually means for us. So let's go back here. So what is normally introduced now is something which is called mini batches. And in the stochastic gradient descent, what one does is, instead of evaluating, if you think now of your cost function, which contains all the small contributions for each data set which you have, what you could do now is, instead of calculating the gradient the way we have done till now, where we run over all the data points. So just keep that in mind, that till now, we have been calculating the gradients in this specific way. So what you could think of is to reduce some kind of introduce some kind of stochasticity or randomness by only taking gradient on a subset of the data. And this subset of the data is normally called mini batches or just batches. Sometimes we just skip this name, mini batches. So if you have something like n data points, and then a size of each mini batch is m, then there will be something like n divided by m mini batches. So if you have 10 data points and you have 5 batches, then each batch will contain only 2 data points. Okay? So normally this mini batch is something you would call for B of k. And as an example now, suppose you have 10 data points. If you choose 5 mini batches, then each of them will contain x1, x2, up to some x10. You would often reshuffle the data. And then when you run the experiments now, instead of making a run over all the data points, you actually have a run over all these batches. So that means that a gradient descent step would now look like something like this. So you have the parameter beta, which gets updated. You have a learning rate here, which we can keep fixed or we can change it. And then we take the gradient over these specific batches. Now, one thing we're going to look at, I'm going to skip some of these codes, but I'm going to show you how you can actually set up such a code with a number of mini batches, which you can vary as a parameter. So what you can have now is the same case as we had before, a simple function, linear function. And we do the standard ordinary least squares as we've done before. So the first part is just the same. But now we define a set of mini batches to be 5. And now we define something which is called an epoch. So this is the number of time we rerun this experiment. So every time we do a mini batch, this is actually less expensive than calculating the full gradient. But then, since you're doing this in a stochastic way, what we need to do now is actually to repeat these experiments. And this introduces a new parameter, which is called the epochs. So this is a standard naming in the machine learning literature. So when you're going to write your own stochastic gradient descent, you're going to introduce 2 new parameters. And you need to study the stability of the calculation of the gradients with respect to these 2 parameters. So you will have 2 new hyperparameters. So last week we introduced the learning rate. And then for Lasso and Ridge and for most other methods, we have this L1 or L2 or other types of norms, which introduce a parameter lambda. And if you now look at the code, this essentially includes the basic elements. And the basic element which you see here now is a loop, an outer loop over the number of epochs. And then we decide on the number of batches, which is in this case is equal to 5. So that means that the number of data sets which we have in each batch is m here. And what I've done here is simply now to pick a random index where we now shuffle randomly and find the starting point. So this x of I, where we started the design matrix, is given by this random index plus m, which is then the size of each mini batch. So each mini batch has only 5 data points. Okay? So this is the number of data points I put in, which means that when I calculate the gradient here, instead of dividing with the total number of data points, I need to divide with the number of mini batches, or the number of data in each small batch. And then what you see here, what follows here, is simply your ordinary least squares gradient. Now, later, when you introduce automatic derivation, you don't need to deal with you hard coding the expressions for the gradients, because then you just give the expression for the function you want to evaluate the derivatives of, or the gradients of. And so this stochastic gradient descent is actually nothing but this method which you see here. So you run it over the number of batches. So this is a number of mini batches. And each mini batch has, in this case, 5 elements. And these become parameters which we need to play around with. Now, there is an additional thing here in this code, which I will come back to. In this case, there is a slightly more advanced brute force way of updating the learning rate. So you can fix the learning rate for every iteration you do, just have it fixed, or you can update it. And there are many ways by which you can update it. So in this specific case, I have a small algorithm which I call learning schedule. And in that case, what I've done is actually to update my learning rate with an algorithm where I now have a learning rate which gets changed according to this formula, where T0 and T1 are parameters which you need to fix. Now, this is not very elegant, and it's something which has been abandoned. You could also have an exponential decay, or you can just keep it fixed and just let it run like that. Now, the way we would change this now, this learning rate which you see here, is by more advanced methods called adaptive gradient, root mean square propagation, and the method which is mostly favored in the literature, which is called ADAM, which is adaptive gradient with momentum. And these are methods which we will discuss right after the break, so that you can see how we implement them and what they actually stand for. Now, the thing is that we can set up this update of the learning rate in different ways. If you can calculate a Hessian matrix, you would never do this, because then you have the Hessian matrix and you invert it, which means that you don't need to set in a learning rate. Or you can find some cheap recipes for updating it, iteration by iteration. Or we can use these methods, which now are a compromise between not calculating the Hessian matrix and inverting it, but bringing in information about the gradients in the update of the learning rates. And these are, this defines tons of methods, but the three most popular ones are ADAGRAD, adaptive gradient, root mean square propagation, and the so-called ADAM method, which we will discuss after the break. But essentially, this stochastic gradient descent means that we introduce two new parameters, the number of epochs and the number of batches, and our results will depend on that. Now, what you can see here is that the own inversion gives this. If I perform the calculation with my own gradient descent for ordinary least squares, this is what I get. And now I take the results from my own stochastic gradient descent. And in this case, since I'm running this in a stochastic way, I'm not going to get exactly the same parameters as we want to. So how close you get depends then again about the number of epochs and the number of mini batches you've chosen. And these become parameters you will have to play around with. But this is a standard recipe which is used in the evaluation of essentially all deep learning algorithms. But sometimes you may find in the literature people who state that we just used gradient descent, although we know that stochastic gradient descent in general gives better results, and we don't understand why, but this is what gave the best results. So this may happen. But a standard gradient descent is in general more time consuming, because if you have a huge data set and many parameters, this is going to take a lot of time. So you can see there are also discussions on, in above code, we have used replacement in setting up the mini batches, which is actually something you see in this code here. So this rand int actually replaces the numbers. So this is randomization with replacement. And there is a lot of discussion in the literature whether you should do that or not. So if you follow this link, take a look at that one. And there is a discussion on alternatives to the codes which I have presented. So keep in mind that there are lots of kind of practitioners' approaches in machine learning. And sometimes people just suggest a method and it works seemingly, and we don't have a deeper understanding for why they work. Okay. So last week, we discussed this momentum-based gradient descent, so I'm not going to repeat that one. And we went through the derivations of these parameters. And then we ended up with this recipe where we simply have information from the previous cases. And then we weight the new value with the values from the previous cases. Now, one of the things which we're going to discuss after the break are methods like ADA-grad, root mean square propagation, and the ADAM optimizer. So if we look at the codes here, which will be the topic after the break, what I've done here is to take the algorithms from the textbook by Goodfellow et al. And in this case, the parameters are labeled as theta. And what you have here is an update of the learning rate, which is given by this formula here, where you now introduce information about the gradients. And this is now used to update the learning rate instead of having either static learning rate or some simpler recipes for the learning rate. So after the break, we are going to look a little bit more closer into these algorithms. And there is another very popular one, which is called root mean square propagation. ADA-grad is an algorithm which works extremely well with the convex functions, but it's not always the case that we have convex functions. And finally, there is the algorithm ADAM, which, as I mentioned some times ago, is an algorithm which was proposed by King Ma and collaborators, and it has close to 200,000 citations in 10 years. And as I said, a good scientific paper has something like 100 citations. So these are orders of magnitude. This person, King Ma, who proposed this algorithm, also invented a very popular generative method, which is called variational autoencoders, which has another 50, 60,000 citations. So if you've done that, you can actually lean back and rest. But this is a very active person, and he's also very young. Yeah. I just have to take off his headset. Yeah. Yeah.
Is this the way of solving it?
It's partly one way of solving it. So one of the things with the gradient descent, as we said, just to repeat the question, is that every direction is scaled by the same constant. So what we are doing now is that by introducing this information about the gradients, is that every parameter beta which we have will get a learning rate which is different. So in that sense, we are trying to, by introducing this information about the gradients, we are trying to bring in, instead of evaluating the Hessian matrix, which would give us a dependent a learning parameter, which depends on a specific variable. We are now trying to cheat a little bit by just bringing in information of the gradients only. And that will change the direction each parameter beta moves in. If you just have a constant, then all the gradients of the parameters beta change by the same constant. The gradients can be different, but the parameter lambda or no gamma, which we multiply them with, the learning rate, will be the same. And that's something which can slow down considerably the search for the optimal values. So hopefully this one is a recipe which allows us to converge faster to the minimum for each parameter beta. Okay? But you see now that this is actually the delicate problem of all machine learning, the optimization part. And there is a lot of, error and trial, where you try to find different recipes which still are fast numerically, but which gives us perhaps a better estimate of the minima, which we are searching for. Okay. We'll take a small break. Is that okay with everybody? So in order to try to demystify what is going on here, let's now take a step back and look at some simpler cases. So what we are doing now, if you look a little bit closer at this ADA-grad as an algorithm, is that we are trying to change this learning rate for every iteration we make in order to find the optimal parameters. So let's take a closer look at a typical way by which we could implement this in a simpler way. And this is goes back a little bit to one of the examples you find in the slides. So let's exit the full screen and go back to the whiteboard. So if we look at this updating the learning rate, this is one of the big issues, and we do this because we want to avoid to calculate the Hessian matrix. And one of the recipes which you have seen is just to have a constant learning rate, which we call gamma. And we just keep that one constant throughout the calculation. So as we discussed right before the break here, one of the drawbacks with such an approach is that every gradient will be weighted with the same value. So there will be no change irrespective of direction. And the directions are the ways each parameter beta moves as a function of their gradients. So another alternative is to have an exponential decay. And you will see in the literature that people have been trying different approaches here, exponential decay. And in that case, you would simply have a learning rate which gets updated. So this is a gamma, not a y. A gamma of k, which is given by some gamma 0, which would be the initial value, multiplied with some exponential, where you have some new parameters, a parameter k times, so k is the number of iterations which you have performed, multiplied with some gamma of tau, where gamma of tau could be a parameter which you set. So gamma of tau is a parameter. So that gives us, as a function of the number of iteration, it gives us a recipe for updating this learning rate. Now, one of the recipes you will find in the Jupyter Notebook is something which is called a linear recipe. And this has also been implemented historically. So let's just put it up here. So we have a linear recipe. So we would have a gamma of k, which is the updated value, which is given by some 1 minus alpha, which is a constant. Alpha is a constant. And then we have this gamma 0, which is the initial value. So you would typically start with a given guess. This parameter gamma is, alpha is something you would fix. Then you have plus some alpha multiplied with a gamma of tau, where again, this gamma of tau is a constant, as before, is a constant or a parameter. And how you choose it will obviously influence the calculations, but often this gamma of tau, a typical approach you would see is that this is given by 1 divided by 100 times gamma 0. So what does that mean? So suppose now that you make a grid of gamma values, where the first one could be 10 to the minus 5, then you have 10 to the minus 4, 10 to the minus 3. So that means that if you start with 10 to the minus 3, these values get reduced till you come to this gamma tau, which is 10 to the minus 3 divided by 100. So it's a way to reduce the value of the learning rate. But these are very much ad hoc methods, and it's not a guarantee. There's no guarantee that this reflects properly the way these gammas should be reduced. And you will see in the literature that people have been using many such different recipes here. And gamma 0 is often then set to some initial values. So you would typically select a gamma 0. There are many other methods of this more ad hoc way. So select an initial gamma 0. And typically you would have a grid of values. So you could have a gamma 0, which now contains values 10 to the minus 5, 10 to the minus 4, and this goes all the way up to 10 to the minus 1, for instance. And then you would then set up new values according to this iterative scheme. And you would have to define this parameter alpha, and you would also have to define this parameter gamma of tau. So alpha, which you see in the equations here, this alpha here, this becomes a new parameter, and the same with this gamma of tau. Now, there are many, many other recipes, but we are not going to look so much into these details because the kind of dominating methods now are ADA-grad, adaptive gradient, and then we have root mean square propagation or just RMS plot. And finally, we have ADAM. And then we have different variants of these methods. And there's a lot of research on how to update this information about the learning rate in the best possible way. But keep in mind that these are all approximations where we try to find a better way of finding out how the gradients actually move according to the parameters beta. So if you look at ADA-grad, so let's just set it up. And this is a method which works extremely well for convex functions. And you will see examples of that a little bit later. So what you would typically do then is that you would require, so this would be the way you would initialize it, require a learning rate, initial learning rate. So this is the initial one. Initial learning rate, gamma 0. You would have to initialize a guess, initial guess for the values of beta you want to find, of beta 0. You also need to set a constant, which we call delta, which is a small constant, which is added for numerical stability. So constant, which we call delta, which is normally small. So 10 to the minus 8, 10 to the minus 6 for numerical stability in case you have divisions by 0. Or this is a constant for numerical stability. And then we would then set up a while loop while stopping criterion not met. Not met. So which normally is taken, evaluated by taking the difference between the parameters beta, the new values, and the previous ones. And then you would take the expectation value of all the betas, and if that number divided by the number of betas is smaller than a certain quantity, then you would stop. Alternatively, you can look at the gradients, but that means that you would have to reevaluate the gradients, and that's more expensive computationally. So the cheap quantity to evaluate computationally for every loop is the difference between the new values of beta and the previous ones. Because if you take the new values of beta and evaluate the gradient, that is going to require more cycles. So you could obviously calculate the gradients, but as I said, this requires more cycle. Then you can use this irrespective of stochastic gradient descent or plane gradient descent. So you don't need to look at this with only stochastic gradient descent, but you can apply this to any of these approaches. So what you could have here is with stochastic gradient descent, SGD, or without. And in the examples in the lecture notes, you will find examples of both cases. So let's just leave that out. So the next thing you will do now inside this loop is to compute. If you're doing a stochastic gradient descent, then you need to set up the number of mini batches and the number of epochs. So you compute the gradient, which we just call G. And this is now evaluated for a given iteration. And that is obviously calculated at beta of I. Now, there is something which is called now this accumulated squared gradient. Accumulate squared gradient. And I'm going to call this for an R of I plus 1, which is given by the previous value. So this is a quantity we need to initialize, plus the gradient times the gradient. And this gradient is obviously evaluated at beta of I. And this is not an inner product, but it's a component by component calculation of the gradients. And this is normally called the Hadamard multiplication in the literature. And I'm coming back to that. So this is a component by component multiplication. Yeah. So that is my attempt to write the letter R.
R.
Yes. So you mean this one, right? Yeah. That is my best attempt ever of writing the letter R. Sorry for that, guys. I don't think I qualify to become a medical doctor yet because I think my handwriting can still be read. So the next step, which we do now, is to compute the updated learning rate. Compute, update of gamma. So we would have a gamma of I now. So let me just, since I used I for these iterations, gamma of I, which is simply given by gamma 0, the original one, divided by this delta. And remember now that this delta is a small parameter, which we plug in order to avoid divisions by 0. So delta could be 10 to the minus 8 or 10 to the minus 6 or similar. And then we have plus the square root of this quantity R of I. So again, this is my attempt to write the letter R. And finally, we update beta of I plus 1 equal to beta of I minus, and now we have this updated learning rate, gamma of I, multiplied with the gradient which we had at beta of I. And this is end while. So this is the Ada-Grad method. And if you go into this textbook by Goodfellow et al., you will then see the discussion of these different methods. So what I'm going to do now is just to switch back to the slides, because there we have the root mean square propagation in a condensed way, and there are only small changes from one to the other one. This method works pretty well if you have convex functions, as you will see in some of the examples a little bit later here. So if you now go back to what we had here, this kind of simpler method, like an exponential decay or linear update, they all involve some kind of way by modifying where we modify the learning rates, except that these simpler ones, the three first simpler ones, they don't have any information about the gradients. So Ada-Grad is a way to simply bake in some information about the gradients. So that what we are doing now is simply to reduce this gamma 0, which we start with, and make it smaller. And every now, how to say, iteration which we do will now give us a gamma which will be different for the different parameters beta. Now, you may now say, why does this make sense? Now, there is something which is a little bit more delicate, which we haven't discussed and which we will not touch upon very much. But you can evaluate this Hessian matrix by only looking at the diagonal elements. And the diagonal elements will be proportional to the derivatives, the gradient times the gradient. So it's a way to bake in some information about the Hessian matrix, but in a very cheap way. There's something which some of you may encounter, which is called the Fisher information matrix, which is an approximation to the full Hessian matrix, but where you would actually include only the diagonal matrix elements, which would be the second derivative of your cost function, which is not exactly the gradient times the gradient, but it's something which tries to mimic that specific quantity. So one thing we're going to do now is to simply move back to the Jupyter notebook. So let's try to do that. Next time here, I should actually try to find a way to better access my screen. Okay. And now we go in a full view. So the ADA-grad, except for the naming which I've chosen, so the parameters beta are replaced by theta, and this is the algorithm which is taken from the text by Goodfellow et al. In chapter 8. That's actually a pretty good read if you want to read more about these different methods. So we have this small constant, which could be 10 to the minus 7, 10 to the minus 8. We have the global learning rate. So we calculate the gradient. So this is an element-wise multiplication. And then we divide with this accumulated gradient. And this will change our learning rate for every iteration which we make. And then we have the final update here. Now, the only difference between the root mean square propagation and ADA-grad is actually that we have some kind of memory when we calculate this accumulated gradient. So there is a parameter which we now have to include, which is this so-called decay rate rho. And if you think back to this momentum gradient method we discussed last week, you see now that you will have a parameter rho between 0 and 1, so that you actually scale the previous iteration and the new one, which is now given by the gradient times the gradient. And then we calculate this update of the learning rate, again by the same element-wise multiplication. And where this square root of r now is now given by a new expression. So instead of having r minus g times g, we now have this parameter gamma, no, rho, which is typically set between 0 and 1. So many of these methods are very easy to implement, and you will see the codes a little bit later on how we can implement it. So this is something which you can do yourself, or when you later use libraries like PyTorch or TensorFlow or similar ones, you can then just specify the way you update the learning rates. So you would then specify whether you use ADA-grad or root mean square propagation or ADA. So these are methods you can specify, but in the project, we actually want you to play around a little bit yourself with these methods, because it's very useful to see how they function, because when you have programmed them yourself, then you see where the possible bottlenecks are. And as I said, if you can make improvements on Adam, something which works even better, you will get many new friends, and they will cite you, definitely. Now, Adam, on the other hand, is just summarized here. So that introduces two new parameters. So we have rho 1 and rho 2, which have been tuned to some specific values. So there are actually some suggested defaults from Adam, the paper by Kingma. And there's a suggested default value for the step size. And in this particular case, we initialize again the parameters. We have the small delta. We now initialize two moments, S and R. So you can have mini batches or not. You compute the gradient, and then you update the number of iterations which you're dealing with, which is called time step here. And then you have a first moment, which is this variable S, which has this same type of expressions as in root mean square propagation. This contains only the gradient. And then it has a parameter R, which contains the gradient times the gradient. But now it's scaled with a new parameter ρ2. You calculate something which is called the first bias, and then the first bias, the correct bias in first moment, and then you have the second moment, which is this R. And then this S and R are combined to give the final update for the learning rate, where now you have a denominator and a numerator which change. So this is in essence just another way of bringing in information about the change of the learning rate as a function of iterations. So if you go into the some of the original papers, you will see that sometimes people have just proposed a recipe and then played around with it and they see that it works, and later people try to understand why it works. So we are not going to much more into those details here. So when you are setting up a stochastic gradient descent, there are some basic things which, some practical tips. First, you would randomize the data when making mini batches. So you would shuffle randomly the data when forming these mini batches, because else the gradient descent can fit spurious correlation resulting from the order in which data is presented. Transform your results. So try to scale your result by some standardizing the inputs, as we have been discussing before. You have to monitor the out of sample performance. Always monitor the performance of your model on a validation set. So in our case now, we are getting more parameters. And these parameters are the epochs, we have the learning rates, we have the lambda parameters, we have the number of epochs and the number of mini batches. And then we have also the number of parameters which define either Adam or root mean square propagation or ADA graph. So as I said in the beginning, when some people see all these parameters, there's a kind of feeling of disappointment, right? Because at the end, you're just tweaking different parameters. Now, when it comes to root mean square propagation, this is something which has been pretty well tested, and the same with Adam. And the parameters which they suggest are typical parameters which work pretty well in these calculations of gradients. Now, one thing I want to do now, before we look at automatic differentiation, is to look at the examples on how we implement these algorithms. And this is something which becomes relevant for us in next week. So I'm going back now, as I'm jumping a little bit, and I will go back to automatic differentiation, because I wanted to switch over to the Blackboard. And I wanted to say a little bit now about the codes which we have. So when you scroll down here, one of the things is using this automatic differentiation with ordinary least squares. And you see now that the only thing you need to do is actually to set in your cost function, the function you want to calculate the derivatives of. And using automatic differentiation, you simply transfer the name of the function, and that defines an object, which is your training gradient. And in this specific case, I've now changed a little bit the notation. Instead of beta, I have the parameter theta. And then you see now that these parameters theta here get updated by minus eta with the learning rate times the gradients. So this is a typical example on how you would include automatic differentiation, and makes life a little bit easier. You can do the same with momentum, and these are the momentum codes. And in that specific case, if you look down here, you have now a calculation of the gradient. I have defined this delta momentum, which we discussed last week and in the beginning of the previous lecture. And now we have a change which takes into account information from the previous step. So I multiply eta with the gradients, the learning rate, and then I have this delta momentum times the change and the previous change. So I typically initialize that to 0. And then I calculate a new change. And then I keep updating my parameters theta, as you can see here, in terms of this new change here. So this is just a standard gradient descent, but with the momentum. And with momentum, what you would see then is like, if I don't do momentum, just a plain gradient descent, I need roughly something like 30 iterations before my gradients are still not yet 0. Whereas when I do momentum, you can see now that my gradients are by 2 orders of magnitude closer to 0. So dealing with momentum is something which we would include anyway when we do ADA-grad. So you can do ADA-grad with and without momentum. But when you do root mean square propagation, you have actually baked in, and the same with ADA. Here, we include a stochastic gradient descent with automatic differentiation. So the cost function is now still the same as before. It takes as argument y, x, and theta. And this is the cost function which we are evaluating as before for ordinary least squares. But now we are dealing with stochastic gradient descent. I'm comparing with standard matrix inversion, as you see here. But then my training is now, instead of calculating the gradients, I simply have the training gradient here. This is the standard gradient descent. And then what follows here is the standard gradient descent with the mini batches. So I have 5, the size of each mini batch is 5, number of epochs is 50. And then I have this linear learning rate, which we discussed in the beginning of the lecture, which is a kind of very much ad hoc recipe. And if I run this code here, you will see now that the own inversion gives this. And you see now the theta from own gradient descent gives essentially that value. But when I now do the stochastic gradient descent, I'm not getting exactly 3.0855, but I'm getting 3.8077. And these results will change a little bit depending on the number of epochs and the sizes of the batches. So I'm going to skip some of these, but I'm going to, because I put in many codes here, but now I'm doing the same code with the same system with ADA-grad. And in this case, I take another function. So this is, again, the ordinary least squares function. If you have a lasso regression or ridge regression, you would then have a different cost function. That's the only thing which would change. And the same if you do logistic regression, you would just have to specify a different cost function, which depends on different variables. And the variables here are given by your inputs and outputs, y and x, and the parameter theta, which is the same as our old-fashioned, old well-known beta. I set up the gradient, but here I include gradient descent, but with ADA-grad. So I'm actually running a loop over epochs. And for every batch which I have, I implement now ADA-grad, where first I calculate the gradient, but now I have to be careful because the gradient needs to be scaled by the number of data points in a given batch. My automatic differentiation gives me the gradient training here from training. I'm including all data for training. And then I do the update by calculating the gradient times the gradient. So this is an element-wise multiplication. And then I divide by the square root of that quantity. And this gives me now the updated value for theta. And you can see now that in this particular case, even with a gradient descent, I'm actually getting spot on the results which I should get. So I should get 2, 3, and 4, which are the coefficients. And with my other adaptive gradient, I get roughly 2, 3, and 4. So that's an example of how you could implement adaptive gradient with stochastic gradient descent. But you could do it without stochastic gradient descent. There is nothing which hinders you from doing that. Then the examples which follow here gives you a similar example with root mean square propagation. So this is my own implementation. Actually, I haven't tried that, but maybe somebody could try ChatGPT and ask, write me a code for root mean square propagation. I tried this with logistic regression, and it gave a pretty good code. So that's pretty neat. Many of these algorithms are pretty simple. I normally prefer writing them myself, but if you're a little bit in doubt, I mean, you can always try ChatGPT, and that's a very helpful resource. So when I wrote these codes, ChatGPT didn't exist. But what you would do then, you would have to fix these parameters. So we are having a learning rate. We start with 10 to the minus 2. And now you see the number of parameters here are getting many. So this is the root mean square propagation, which I compare to ordinary least squares with my matrix inversion here, or the design matrix, as you've been implementing in the project. And now I calculate again the gradients with automatic differentiation. And I need to specify the number of epochs, the number of data points in each batch. I need to specify the learning rate. I don't have the lambda parameter because I'm not doing ridge or lasso. I specify this rho, and I also take this delta, which is set there to avoid the calculation or the, in case this accumulated gradient is 0 or a very small number. Then I shuffle my values and I calculate the initial and final values for the design matrix or the variables there. The same with my y's. And then I calculate the gradient. And then I implement the root mean square propagation where I have my accumulated gradient, which is given now by this parameter rho, times the previous value, plus 1 minus rho multiplied with the new two gradients. And then my update is now simply given by the gradients times the original value divided by this expression. And again, you see that if I use root mean square propagation, I'm getting a pretty decent result. I could rerun this one. And you see now that every time I rerun it, if I have different random numbers, then I will get different results. But you see again that this result is pretty okay. So to the roughly the third and the fourth digit, I'm getting something which is pretty close to what I would get from exact matrix inversion. And Adam, the final algorithm, is, and the one which many people tend to use or prefer to use, that contains two new parameters, which are called beta 1 and beta 2. It has the learning rate again, epochs, and the number of data in the batches. But now it calculates this first moment and the second moment. And here again, what I've simply done is to implement the algorithm as we saw it in that specific case. And you see, again, in this case, I'm getting pretty close to the values which I get from matrix inversion. And in this case, I have a data set which doesn't have any noise. So ADAGRAD, root mean square propagation, and ADAM are methods which allow us to update the learning rate. And what you will often see in the scientific literature is that people have tried all three of them. And then they will simply say that in this specific case, ADAGRAD seemed to give a better result. And often you don't know whether your function is a nice convex function or not. So that's a very important thing, because when you apply these methods, you don't know whether you have a convex or concave function, or whether you can be stuck in a saddle point, or you can be stuck in a local minimum. So that's why people try different methods in the runs. So a deep learning calculation, a neural network calculation, involves often many numerical experiments. So you would run with the learning rates, different learning rates. You would run with the different ways to update it. You will run with different hyperparameters lambda. You will have different epochs and different mini batches. And all these are parameters which lead to some kind of experimentation, where at the end, you have to settle on the best possible parameter for your data set. Okay? I guess it sounds a little bit disappointing, but a typical deep learning calculation with a neural network or convolution neural networks means often fiddling around with many parameters. So that means making many runs. Any questions so far? So there are some additional codes on where you implement the same for logistic regression. But what I wanted to do now is to say a little bit about automatic differentiation, because this is something which most of you have not heard of. Is there anyone here who's heard of automatic differentiation? or used it? Only one. And that's pretty common. And this is actually a central algorithm because you saw from all these code examples, which I gave you as a kind of teaser, you see now that I did not need to evaluate the gradients, or actually not evaluate, that's wrong. I did not write down the analytical expression for the gradient, and I did not have them in the code for the gradient descent. So I simply use either automatic differentiation through AutoGrad or through the new library, which is called JAX. And you can find examples on how to use JAX down in the slides here, and we are coming back to that. But what I want to do now is to switch back to the whiteboard and say a little bit about what's behind automatic derivation. So we will not get time to look into our first encounter with neural networks, and we will postpone that to next week, which also fits well because next week we are going to start with project number 2, and that is about you first writing a code for gradient descent for logistic regression. And then we are going to increase that to a neural network, which does a classification problem. So let's switch back to the whiteboard, and let's start looking at the automatic differentiation. As I said, my pointer, there it is. There we are. And this is actually it's a very it's a technicality, but it's an extremely useful technicality. And if you have to deal with the calculations of derivatives in your thesis work or in other connections, this is the technique you would use in case you can rephrase your problem in terms of elementary functions, but you can also actually take the derivative of a function, of a program. I'm coming back to that. So let's now look at the topic automatic differentiation. This is the repeated operation with a chain rule on elementary function, which allows you to calculate derivatives to really to numerical precision. So let's look at an example in order to gain some kind of a feeling for what this is about. So let's start with that and a simple example. And let's now assume that you have a function f of x, which is given by the exponential of x squared. Now, we all know how to calculate that one, but what we could do now is to rewrite that one in terms of a new variable, b, which I also call for the exponential of a, and where I have defined a to be x squared. So this is often set up as a graph, as a computational graph. And the reason for why we set it up as a computational graph is that we are going to set up neural networks as computational graphs. So you can now think of us feeding in some variable x. So what you would have now is x, which goes into a. So what you see here is an example of a computational graph. And a goes into b, which then goes into f. Okay? And this is something which we are going to look at again and again and again. So if you think back to what we did with logistic regression, so just to give you an example, this is a small aside. When we had logistic regression, we could have data sets like x1, y1. This is the NAND gate which we had. We had x2, y2, x3, y3, and then we could have up to an xn or yn here. And these are points which then feed into some function, which in our case was the sigmoid function. So they all feed in here, and they produce a specific output. It could be just one point, or it could be several points. So it doesn't need to be only one output, but we could have many outputs. And essentially, when we think of a neural network or logistic regression, we can set up what's called a calculational graph. So when we are calculating the gradients, what we do then here is that this output goes into, and let's call this output for z. This goes into a cost function, which depends on z, and it depends on the observations which we have, which we can call for t for the target value. So this is the observation. And then we have some parameters. And let's just call these parameters for theta. So these are our parameters. Now, what we are doing now is that we are calculating the gradient of this function c. And we want to optimize that gradient with respect to the parameters theta. So what you have here is something which is essentially a graphical illustration of what we have done till now. So we feed in some output into a function, which we use to evaluate whether this is a good model or not. And this depends on the outputs or the target values, t, which we previously called for y. And then we have some parameters, theta, which previously we just called for beta. But now they can represent different quantities. So when we fitted the parameters beta, we were thinking of, like, let's say, a polynomial fit or some other types of function which we are fitting. But now these theta could encompass more variables. And later for neural networks, we are going to call them for biases and weights. But now theta is a common denominator for the unknown parameters of the model. This is essentially what we end up doing. So if you now look at what we have here, you could think of this f as the function we want the derivative of. So we want the derivative here of the function c as a function of these parameters theta. So in one way or the other ones, we need to calculate derivatives. Now, in this specific case, this quantity here is a little bit simpler because there's only one intermediate step here, which produces these values z. But we will have to use a chain rule here as well. So let's look back at this example which you see here. And now we are interested in the derivative of d of f with respect to x. So we want df dx. And you see now that with this simple function, we can write this as a d of f of db. And notice one thing here, that this is actually 1. So the final step is always 1. And you see that immediately here because f is equal to b, right? So if I take the derivative of f with respect to b, that is equal to 1. Then we have a d. So this is essentially just the chain rule. So automatic differentiation is us applying the chain rule repeatedly. And if we look at these expressions, this is nothing but 2x, and this is nothing but the exponential of a. So automatic differentiation works best when we can break down what we have in terms of elementary simple functions. And this is also one reason for why many of the functions we deal with in neural networks are given by, like, say, the sigmoid function, which gives simple derivatives in terms of exponentials, a tanh function as an activation function, and other simpler functions. Now, I'm going to just say one more thing. If we now look at these derivatives, and this is what we will start with next week, there are two ways of setting up these operations. So I can write it like a df, db, and db, da, multiplied with dA, dx. This is called a reverse mode. Or I have my df, db, with db, da, and da, da, and dx. And this is called a forward mode. So it depends on where you start evaluating the derivatives. In neural networks, and this is something which many people don't know very well, but probably many of you have heard about the backpropagation algorithm. Have you heard about that? That's the famous algorithm by which you train the parameters in a neural network. The backpropagation algorithm is mathematically the chain rule applied in a reverse mode. Nothing more than that. So the backpropagation is automatic differentiation in reverse mode. And the reason for that is that if you look at this graph here, you have many, many input variables. So you could start calculating the derivatives in the forward mode, but then you often have many variables. However, your output is normally consisting of few variables. So you would start evaluating matrices to calculate the derivatives with by just looking at fewer variables. And that's why when you train a neural network, you actually train it by setting up the gradients backwards in the reverse mode. So at the end, what you want is a derivative of this quantity which you see here, the c as a function of these parameters, where you have initialized these parameters in one way or the other one. So you propagate through the network with some initial values. And then, since you have fewer variables here, there are gradients of lower dimensionality. And then you propagate back and train the gradients till you then have new values for the gradients. And then you set up new values here. And then you go back and forth this way till the final gradients don't change by a fixed amount. So backpropagation in neural network, which we will encounter next week, is nothing but automatic differentiation in reverse mode, where you start looking at derivatives by picking the endpoint, which is that you start here. We are going to look at more examples, and we are going to build up a neural network code gradually over the next 2 to 3 weeks, so that you have all the entry points which are needed to set up your own code for a neural network. But just if you can keep that as a message, the central algorithm is automatic differentiation in the reverse mode. And next week, we're going to practice and look at more details.